Hi, so the next pattern in the series is how do metals react with acids? And to deal with that, I need to explain to you first, and you need to understand what acids are and what salts are. Now, salts is not the same as salt you put on your fish and chips. The chemical term salt is specific, and I need to explain that. So first, let's start with some common acids. 4 common acids typically. 3 of them are much more common than the last one. Hydrochloric acid is the most commonest of all the acids. Sulfuric acid and nitric acid. They're the 3 acids we have lying around the labs. We do all kinds of experiments with those 3. And then we have an organic acid, which you might know as vinegar. Pure vinegar is ethanoic acid. And every now and again, you have to know about ethanoic acid. So if we look at the formula of these, then HCl is hydrochloric acid, H2SO4 is sulfuric acid, HNO3, nitric acid, HCH3COOH. That HCH3COO, I'm trying to point out to you that all of the acids contain hydrogen. I mean, it's a fact. There can't be acids if they don't have hydrogen in them. Later, we'll deal with a topic on acids and we'll explain why. But for now, just know that acids have got hydrogen in them. And starting with that idea, what if you've got a metal? When the reaction happens with a metal, the metal replaces the hydrogen. So if you have a metal, and if there's a reaction, the metal will displace the hydrogen in the formula. So if a metal goes in there instead of hydrogen, then that will be a salt. Metal goes in there instead of the hydrogen, that will be a salt. So metal going wherever the hydrogens are in the formula of an acid, that gives you what a salt actually is. Now, let's get you to learn the idea of what a salt is. The idea of a salt is whenever a metal replaces the hydrogen in the formulae of any acid, then we have a salt. For example, say you pick the metal called sodium, and say you've got hydrochloric acid. Well, if you put sodium there, instead of the hydrogen, the sodium there would make it sodium chloride. Sodium chloride is a salt. Now, that happens to be the salt we sprinkle on our food and put it on our fish and chips, etc. But it's just one of thousands of salts that we have in chemistry. The sodium chloride, household salt, is a chemical salt, but there are many others. Now, pick a different metal. What if we got a metal like copper? And what if we were to put copper as the metal in place of the hydrogen? Well, copper chloride would have a formula that would be CuCl2. Copper chloride is a salt of that acid. And what if you got like a different metal? Silver. Silver, in place of the hydrogen, say of sulfuric acid, would make silver sulfate, and silver sulfate is a salt. In the same way, what if magnesium replaced the hydrogen in nitric acid? Then magnesium nitrate would be a salt. What if gold replaced the hydrogen in vinegar? Well, then gold ethanoate would be a salt. You pick any metal and put it in place of the hydrogen in any acid, then that is the chemical term salt. So if you understand the term salt and you understand what an acid is, then we can proceed to explaining to you how metals will react with acids in a general pattern and giving you a general formula. So what is the pattern, or what's the general equation for metals reacting with acids? Well, first I want you to understand that not all metals react. It's a bit like the pattern with water. there are metals that do not react with water. In the same way, there are metals that do not react with acids. And those are the metals, you should be familiar with these. They didn't react with water. They are the coppers, the silvers and the golds and the platinums of the world. Those unreactive metals do not react with acids in the same way that they did not react with water. But the metals that are more reactive than copper, they do react, and they react according to the following general equation, this one here. Look, reactive metal, if it's reactive enough, it's got to be more reactive than those, copper, silver, gold, etc. If it's a reactive metal, then it will react with an acid, and it will make this term salt that I've been wittering on about earlier, and hydrogen gas. You need to learn that, and that is the third of our equations, third of our general equations that I want you to learn. And again, the speed of such reactions depends on how high or low on the reactivity series a metal is. So I'm just going to try something now with my surface. I'm going to try with the stylus writing these equations in front of you. So if we talk about zinc and sulfuric acid, let's go back. Have I gone too far back? Sorry guys, I can't seem to write on my surface as the PowerPoint is proceeding. So I'm going to just show you this, and then I'll stop the video and I'll start it again. I'll pause the video and I'll put the writing I wanted up then. But I want you to be able to use that general equation and write specific equations for how does these metals, zinc, magnesium, copper, aluminium, how do they react with sulfuric acid, hydrochloric acid, nitric acid, ethanoic acid? And I want you to write balanced symbol equations for those four. I'll leave that on there for a minute so you know what we're going to do. And then I'm going to pause it. I'm going to put the answers into that. And then I'm going to carry on the recording. So I'm going to try and pause it there. You try and do this as well. Hi, so welcome back. I've just put those things into my PowerPoint. Can we think of these reactions as follows? And try and follow my logic here, it's important. That's a metal, zinc metal. It comes along and it pushes out, or the chemical term is displaces. It displaces the hydrogen. It kind of pushes the hydrogen out of the acid and takes its place. Now, as I've explained to you, when a metal replaces the hydrogen in the formula of an acid, then you have a salt. So that is a salt. The salt is zinc sulfate. Zinc sulfate, that's zinc sulfate. And the hydrogen gas has been pushed out, comes out as bubbles of gas, and we see it as hydrogen gas. So that idea repeats whenever you have a reaction. Now, two totally different combinations here, magnesium and hydrochloric acid. Well, the same thing happens. The magnesium comes along, pushes out the hydrogen. Takes its place. And the magnesium, when it pushes out the hydrogen, will make magnesium chloride. The Cl is for chlorine. Magnesium with chlorine make magnesium chloride. The formula of magnesium chloride is MgCl2. And MgCl2 dissolves in the water. Whenever you've got these acids, we always use them in water. So there's plenty of water whenever you're using acids, because the acids are in water. And that water, the salt, will very often dissolve in that water of the acid, and therefore we need the state symbol AQ to take into account that the salt is in the water. The hydrogen that's been pushed out comes out as hydrogen gas. Now, whenever I set this to my classes, they get this one wrong because they tend to say, oh yeah, sir, the copper is going to push out the hydrogen. We're going to get copper nitrate and hydrogen gas. And of course, that is what would happen if there was a reaction. But copper does not react. And when things don't react, I show it like putting a cross through the arrow and writing no reaction to make it clear that there is no reaction because copper is not reactive enough. Look, the copper tries to come along, push out the hydrogen and take its place. But the copper is not reactive enough to do that. Hydrogen, on the reactivity series, hydrogen is more reactive than copper, and therefore the copper will not manage to push it out. Indeed, any metal lower than copper in the reactivity series will not manage to push out the hydrogen and take its place. So you will not get a salt formed with anything copper and lower than copper in the reactivity series. Now, this is a bit of a difficult equation to write, the last one, but it follows the same ideas. Now, when we do organic chemistry and we explain to you exactly what ethanoic acid is, it's only that hydrogen there that I'm pointing to. It's only that hydrogen that can be pushed out as hydrogen gas. So when aluminium reacts with it, then aluminium pushing that out will make something called aluminium ethanoate. This bracket is the ethanoate ion. And with one aluminium, you need 3 ethanoates to balance it all up. And that's not balanced when I'm looking at that. I've not balanced that, I'm sorry. But look, let's balance it with you now. 2 aluminiums, there's only 1 aluminium there. So you need a big 2 here. What's missing? Where my fingers are. You need a big 2. That big 2 will multiply that formula by a big 2, giving you 2 aluminiums. And you get 6 ethanoates. Well, we've only got 3 here. A big 2 there would give you 6 ethanoates. So put a big 2 there, 6 ethanoates, and then 6 hydrogens would come off as 3 lots of hydrogen H2 gas. And don't worry so much about that equation. It needs a big 2 there, where it needs a big 2 there. So make sure you put that in if you're writing it yourself. But as an intellectual exercise, I think if you understand what's going on, you should be able to do that fairly difficult equation. It's just pushing your boundaries a little to get you to think on your feet a bit more than you would do normally. So I want you to practice. I want you to practice writing equations, different combinations of metals, different combinations of acids, and bear in mind that there are some that do not react. Don't get caught out by somebody trying to ask you to write an equation for a reaction like copper, because copper is not reactive enough. Now, I've got a few diagrams that will help you with your chemistry. Practically, you need to do some of these reactions. Typically, we do them in test tubes. When you drop copper into a test tube of any acid, there's no reaction. Copper did not react at all. When you have something like zinc that's above copper, then the zinc does react. You see quite a few bubbles coming off from the zinc, and it's a steady bubbling that happens with zinc. With magnesium, you see a vigorous reaction. Loads of bubbles of hydrogen come off. With calcium, you get even more bubbles of hydrogen coming off per second. And potassium and sodium would be explosive. If we put them in, we might have so much hydrogen coming off that the test tube breaks. So we don't do that. The reactions with potassium and sodium and acids are too vigorous and dangerous, and we don't do them because they're just too reactive for us to handle. So you need to do some experiments with some metals, dropping them into acids and seeing what happens. Now, can I point you to something here? Aluminium. Aluminium is fairly high up in these reactivity series. And when you put aluminium into acid, it doesn't react. When you put aluminium into water, it doesn't react. You need to know why. We'll come back to that in a minute. So I've grabbed this other image off the internet, which I didn't quite like because it's not quite right. It's not quite correct. Potassium, sodium, lithium, calcium do indeed react with water. That's correct. They react quicker than magnesium, aluminium, zinc, iron, tin, lead. They react, but they react slower. And that's what was missing off this table. But other than that, I like the very reactive down to unreactive. I like the fact that they react with water and they react with acids, and there is a reactivity series that we can develop. In that way we can write those down, and there's a dividing point where copper, mercury, silver, gold do not react. There, that dividing point is what separates these that react from these that don't react with water and with acids. And my next few videos will go on to reaction with oxygen, but they kind of all react with oxygen, except gold doesn't react with oxygen, and we'll come back to the reaction with oxygen later. So I want you to know some kind of reactivity series, and here's a reaction: potassium, sodium, calcium, magnesium, aluminium, carbon, zinc, iron, lead. Zinc, iron, tin, lead, hydrogen, copper, silver, gold. I want you to be able to write most of that in order, in the correct order. Now, I found this on the internet just a few minutes ago. How to remember it? Please stop calling me a careless zebra. Instead, try learning how copper saves gold. And if you look at the first letters, and the first letters correspond to the elements, that might be a way you use to learn a short reactivity series. I in my chemistry when I was your age learnt P, SZ, Mazilk, potassium, sodium, calcium, magnesium, aluminium, carbon, zinc, iron, lead, copper. And that PSE Mazilk, when I was your age, I was told, is the initials of a famous person. PSE is his initials, Mazilk is his name. PSE Mazilk. Learn PSE Mazilk and you can get some kind of short reactivity series. But whenever you're dealing with these reactivity series, please note, carbon and hydrogen are not metals. So they appear in brackets. They're in brackets. They're not metals, but it's good to know their position. You can do a lot of chemistry knowing the position of carbon and hydrogen, even though they are not metals. Well, let me give you one such use. Hydrogen is there. Any metal more reactive than hydrogen will react with acids and water, because any metal more reactive than hydrogen will be able to push out the metal and take its place. It'll be able to do that displacement that I talked about. It will be able to make for you the salt, and pushing out the hydrogen, you'll get bubbles of hydrogen coming off. So the usefulness of knowing where hydrogen is allows you to guess if you know the metal is above or below hydrogen, whether there will or will not be a reaction. In the same way, carbon. Later, when we do year 11 chemistry, we do reduction oxidation reactions. We will need to know the position of carbon to know if we can extract that metal from its ore by heating it with carbon. And basically, anything lower than carbon, we can get by heating it with carbon. Anything higher than carbon, we cannot get by heating it with carbon. And that's something we'll learn later. So I want you to learn all of that now and find some way, make up your own memory aid. Make up your own memory aid or use this memory aid, but in some way, I want all of my pupils to be able to write down a short reactivity series. That's a short reactivity series. You might say, oh, it's not that short. But it is, because there are about 80 different metals. And you can put them all in this kind of order. And you don't need all of them. You only need a short series like this. And then you'll kind of know which metals will react, which ones won't react. And out of the ones that react, you'll know that some react slowly and that some react quickly. So finally, why does aluminium not react? You expect it to. It's fairly high up in the reactivity series. It should react, but it doesn't. Why not? Well, if I were to cut through a lump of aluminium like that, and that was the aluminium in green, well, in red there's an outside layer of aluminium oxide. That the outside aluminium reacts with oxygen in the air, and the outside of the aluminium is coated with an invisible, very thin layer of aluminium oxide, which protects it from water or acids that are around trying to react with it. Now, if you destroy that protective aluminium oxide layer, if you can destroy that, and we can do that if we put acid in and heat it, once that layer goes, then we see the reaction of the aluminium underneath, and the reaction of aluminium underneath is as vigorous as we expect it to be. It's more reactive than zinc, and it's less reactive than magnesium, and it will give you lots of bubbles of hydrogen gas once you destroy that aluminium oxide layer that's around it. But water won't destroy that oxide layer. Acid will, but the acid needs heating, and I will try and demonstrate practically these reactions, and I'll try and show you by heating up aluminium and acid combination that initially there's no reaction, but give it time, and after heating there will be a reaction. And I'll show you the others as well, hopefully. So that's the end of the PowerPoint. And I suppose if I go back, the one thing I really want you to learn is that. That's the third in the series of our general equations. A reactive enough metal, that's above copper, reactive enough metal will react with acid, and it will make a salt by that displacement idea that I've been through, and it will kick out hydrogen gas, which you will see as bubbles, or effervescence is the chemical term. Right, I'm going to stop there and carry on next time with something different.